This is Mrs. Palmer-Quay with the third video for Module 15. In this video, I'm going to talk about Le Chatelier's principle. Let's spend a few minutes reviewing equilibrium. In the last video, I talked about how reversible reactions can reach a point of equilibrium. And in equilibrium, the rate of the forward reaction and the reverse reaction are equal, so that they are both occurring at the same rate, and it appears that nothing is happening. Also at equilibrium, the concentrations of the reactants and the products remain stable, and it appears that nothing is changing. Though I did try to illustrate the fact that even while it appears that nothing is happening, there are still the forward reaction and reverse reaction occurring down at the atomic level. Equilibrium requires a closed system. I didn't mention this in the last video, but you can't be losing anything to the outside environment. It needs to be in the same container so that products and reactants can continue to move forward and in reverse following the two reactions. Equilibrium can be disrupted. You can stress equilibrium by changing the concentration of either the reactant or the products, by changing the temperature, which of course I think you'll be able to figure out how that will affect an exothermic or an endothermic reaction, or also if the reaction involves gases, if you change the pressure, it will affect things. And so Le Chatelier's principle tries to spell that all out. It says that when a chemical system that is at equilibrium is disturbed by a stress, that system will respond by attempting to counteract that stress until a new equilibrium is established. It tries to make things go back to the way it used to be. So let's look at these three things that can stress equilibrium. The first is a change in concentration. Now remember that our equilibrium constant, or the big K, represents a ratio of the concentration of products to the concentration of reactants. It's not a particular number, it is a ratio that it is achieved by doing some division. So that if the concentration of the reactants or the products are changed, the system will work to restore the ratio, and so that your equilibrium constant is not affected by the starting concentrations. In this example, the reaction has been allowed to run for a short amount of time until equilibrium is reached, and there are three substances. We are taking carbon dioxide and decomposing it into carbon monoxide and oxygen in this reaction. So at this point of equilibrium, you can see that there is a certain spacing between the different products and reactants. More carbon dioxide is added to stress on the system, and so you end up with a change so far as how far up the concentration axis these lines are running. But when we are at equilibrium again, you see we've got this same ratio. It's just at a slightly higher level on the concentration axis. So when you're changing concentration, you're not affecting your equilibrium constant. You'll be, if you add more reactant, you'll be making more product, but you're also going to end up with more reactant being left over. And the reaction will seek to reestablish the equilibrium with the same proportion between the different components. Here's a chart that talks about the different things that happen. So if you think about the changes as somebody being on a teeter-totter, that might help you think about how you need to rebalance it. If you add more reactant, then the forward reaction is favored to make more product and balance things out again. If you add more product, the reverse is true. You try to make more reactant to balance things out. If you remove the reactant, then reverse reaction is favored because you are ending up with more product, just like the one right above it. And of course, if you remove the product, then the forward reaction is favored because you've taken away the product, the whole purpose of the reaction, so it wants to make more product to fill in that hole. Moving on now to changes in temperature. You remember from our thermodynamics module that all reactions involve a change in enthalpy, and we typically measure that as a change in temperature, getting an idea of what the heat is, how the heat is moving in the reaction. So that heat can be a reactant in an endothermic reaction. Heat must be absorbed in order for the reaction to occur. Or heat can be thought of as a product in an exothermic reaction. Heat is given off. It's in excess. That energy is not needed anymore. An increase in the environmental temperature then will favor a reaction that absorbs heat, that needs heat to react. It is in that reaction we'd be writing heat as part of the reactants in an endothermic reaction. These two reactants plus heat gives us this product. And of course then the reverse is true. A reaction that is exothermic will be favored by a decrease in temperature. Now, unlike concentration, changing the temperature will change your equilibrium constant because the temperature change has a more continuous impact. If you change the concentration, you're one time adding more reactant. But if you're increasing the overall temperature of a system, it's like you're always adding a little bit more of that reactant or that product, depending upon what would be favored by a change in temperature. So you don't have the same equilibrium constant because it's going to change the rate of either the forward or the reverse reaction to a greater extent than the opposite one, and so the ratio at the end at equilibrium will be different. Here's an example of how the temperature can affect the equilibrium of a particular reaction. In this reaction, we are taking dinitrogen tetraoxide and making it into nitrogen dioxide, and this is an endothermic reaction. Heat is part of the reactants. And so at very low temperatures, our dinitrogen tetraoxide is actually in solid form. It hasn't made its way to the gas, and we've got no color in the tube. At very high temperatures, or certainly much, much higher temperatures, we have this dark brown color of the tube, and that is the color of the nitrogen dioxide. Dinitrogen tetraoxide as a gas is actually colorless, and so the forward reaction is being favored here at higher temperatures because it is an endothermic reaction. And so if you're adding more heat, it is as if you are adding more reactant. And so we're favoring the formation of nitrogen dioxide. But in these medium temperatures, well, it's kind of a little bit cool there, -9 degrees Celsius, we are seeing both the dinitrogen tetraoxide gas, which is colorless, and the nitrogen dioxide gas, which is dark brown. Both are present at the equilibrium state at this temperature, and so that the gas in this sealed tube is a light brown color. Here on the far right, at the higher temperatures, we do have some of that dinitrogen tetraoxide gas because it is a situation at equilibrium, so you have both the forward and the reverse reaction happening. But the favored reaction is definitely the forward reaction at the higher temperatures, so that you could change the color of this tube based on how warm the environment is, and that's showing you which reaction is being favored by the temperature. And finally, changes in pressure. Pressure only affects equilibrium systems that involve gases. And increasing the pressure favors a reaction which would make fewer moles of the gas, because that would thereby decrease the pressure. So that if you're increasing the pressure by your action, your reaction wants to decrease the pressure to return to the original state at equilibrium. So we have a little illustration down here where we've got a certain amount of equilibrium has been reached, a certain amount of reactants and products. If you decrease the volume, you increase the pressure, these molecules are being squashed together in order to make less molecules there. The reaction that favors a fewer number of moles of gas would be the one that would predominate. And so in this case, we've got 2 moles of gas on the reactant side and 1 mole of gas on the product side. And so increasing the pressure for this reaction is going to favor the forward reaction to make more products. Conversely, if you increase the volume, you decrease the pressure by making more space, by spreading those molecules out. Well, at equilibrium, they were closer together, so the reaction is going to favor something that'll put more molecules in there, so there'll be more molecules closer together like it was at equilibrium, and so the reverse reaction, making the reactants, will be favored when you decrease the pressure. Unlike this example, you might have a reaction where a gas is only present on the reactant side or only present on the product side, but you can still use this rule. Pressure will still affect the forward or reverse reaction, depending upon where the gas is found, there you have a choice not between 1 mole or 2 moles of gas, but between 1 mole and 0 moles of gas. So anytime there's a gas involved, even if there's only one compound or molecule that is a gaseous in the gaseous state, the change in pressure will affect equilibrium. The book doesn't use the word going to completion. It just talks about when a reaction cannot reach equilibrium. A more common term to use is to say that a reaction goes to completion, that no equilibrium can establish because of generally one of three things. The overall effect is that the product is removed, or one of the product is removed as soon as it is produced, and so it is no longer available to take part in a reverse reaction, and therefore equilibrium can't be established where you've got the rates of forward and reverse reactions being equal. There are three conditions where we see a reaction going to completion. The first one is the formation of an insoluble precipitate. So we've got some barium sulfate being made here in this test tube, and you can see it's just falling out of solution and will be collecting on the bottom of that test tube. And since it's insoluble, it's not going to be tempted to break apart into ions again and dissolve back into the solvent. And so those components, those molecules and atoms are just out of the picture completely. The second way a reaction can go to completion is that it forms a gas that then escapes. So if it's not a closed system and a reaction makes a gas, that gas can then expand and move its way into the outside environment and disappear out of the solution. So in our second picture, we've got a strip of magnesium that's placed in an acid, and it's making hydrogen gas by loaning some electrons to the hydrogen ions in that acid. So then the hydrogen gas is escaping the test tube, not to be available for reverse reaction. When you mix your baking soda and vinegar, that's a reaction that goes to completion. It makes a great deal of carbon dioxide gas, and it expands and evaporates, or it leaves the container and goes into the environment, the air in the room. And finally, reactions that involve the formation of water, especially when you have ions then that end up being dissolved in the water, also go to completion. You're not able to establish equilibrium. So this third picture is just showing a reaction in progress of mixing sodium hydroxide with hydrochloric acid, and you will make table salt, sodium chloride out of that, and water. And it's just a simple acid-base reaction making an ionic salt and water, as we looked at in your book. But you can see that the attraction between the sodium and the chloride will not be enough to pull apart the water and allow any kind of reverse reaction to occur. It will just dissolve in the water. So the term that you won't see in the book, but I might use it in my own talking, is that these are reactions that go to completion. They are not able to establish equilibrium because at least one product is removed as soon as it is made. So this finishes up what I want to say about Le Chatelier's principle and what happens when you put stress on an equilibrium. This particular concept is extremely important in industry, and that's what allows us to make a number of compounds by not allowing equilibrium to be established, generally by tweaking the temperature and the pressure to push the reaction in the forward direction, and then also by removing a product as soon as it is made so that all the reactants will be used up.